Chenyang Xu, who talked about K-stability and Moduli of Fano Varieties 2.
Okay, thank you very much. So let's continue from where we stopped yesterday. So yesterday I started discussion the relation between test configurations and valuations. And I said that there's a actually precise correspondence between a subclass, which is the LC place. Well, my pen doesn't work now. There's always something. Okay, I don't know why my pen. Okay, anyway, so there's an LC place of complements. One correspondent. That's fine. One correspondent to test configurations have a slightly more general than special, which is we call weakly special, which is basically XX0 is LC, but the fiber is reducible. So special means XX0 is PLT. So the fiber, I mean, is KLT. Here the fiber is irreducible, but maybe similar-canonic. So then we showed yesterday that the runtime side is good enough. Even a smaller class is good enough to tell the K-stability. And then you can imagine, actually I mentioned this yesterday, that the left-hand side is also enough to compute the delta. So you can just compute the delta on all this kind of EM, which comes from the Q complement and take the informer. But then I use Burkhardt theorem to say, if it's a LC place of Q complements, it's indeed a LC place of N complements for fixed N. So I can just look at the fixed N and look at all the complements over the LC place over such N complements and take an informer, then I can compute my delta. But actually I can do even better. I can just take one divider and look at the informer of that divider and then compute delta. A priori, of course, I don't know which complement I look at, but theoretically there exists one. I'll explain why this is true. And the same argument will show actually that the delta invariant is constructible and the lower semi-continuous. So particularly if you look at the locus where it's semi-stable, which is a locus where the delta is at least 1, then it's an open set. I mean, again, prove this open set is quite difficult, but we have it now. So before I go into the proof, let me introduce some notions. So if I have a simple normal crossing over X, and I have some divider lambda with some components lambda I, if I take an intersection of them, I look at the generic point eta z. And then I look at the valuation centered on this eta z. And I pick up one positive number, not positive vector with all the coordinates positive. And I define, which I call alpha. Then I define valuation attached to V alpha to be, for any function f, I look at the expansion of f at the generic point eta z. And then I take this pairing of alpha beta for all the basically monomial z beta show up. So for instance, if I take alpha 1, 1, 1, then that's just a blow up of the divider. And if you take a bunch of other integers, then that's going to be the weighted blow up. But actually, the upshot is I can even take a real number, and I got some valuations, which is not a divisorial, but that's a valuation. And if I consider all this y, all this lambda, if I put them together, I call them comonomial valuation. So here I draw a picture for 3 divider intersect. Then gamma 1, gamma 2, gamma 3, each give me a divider, V1, V2, V3, and the dual complex is how they intersect with each other. So it's a 2-dimensional simplex. And the valuation is the cone over that 2-dimensional simplex. So basically, all the divider centered under this point for gamma 1, gamma 2, gamma 3, that's precisely equivalent to the point in the first octant in this picture, in this 3-dimensional case. So now, as I said, we already know that for delta, we can just compute it by looking at the informer over all the dividers which are LC places of n complements. But here, now I can put all this like n complements together. That's just parameterized by the sections in the minus nkx. And then I can stratify them. Then I have this universal family of divisor dx. And then after stratification, I can assume they have a simultaneous fiberized resolution. So now the base is stratified into disjoint union of a bunch of locally closed set. And then I assume that after this stratification, every fiber has simultaneous resolution. I mean, obviously you can do this. You just resolve the generic point that will expand to a certain open set, and then you know their induction to work on the rest. So now I just pick up one point. So now I work over one kinetic component B. So I pick up one point in this B. So I just pull back Kx plus D. I know it's Ky plus gamma. I write it as Ky plus gamma. But if I have another point, T0 in this B, I pull back the corresponding divisor D0 plus Kx. Then I got Ky0 plus gamma 0. So these are just two different fibers. So of course, because I have a simultaneous local resolution, I can basically identify canonically the dual complex, right? I mean, since I have basically the same combinatorial structure upstairs, I can identify the dual complex. But the upshot is that if now I only look at the subcomplex with coefficient of 1, that's where all the LC places come up. And so these two dual complexes are still identified. So if I have 2 points, so I have 2 divisors corresponding to the same point after this identification, then the S will be the same. So that's a kind of inverse of progeneral result. Because this F and F0 a priori they live upstairs in 2 different fibers, but we know they are corresponding to the same point under this identification of dual complex. Then the inverse progeneral tells us that the SF is equal to SF0. I mean, there still needs some proof, but then it can boil down to this inverse progeneral result I proved with Christoph Hayek and James McKenna more than 15 years ago. So because of this, once over this component, I can move all the divisor just over one fiber. So this way I prove that there's one divisor, right? I can just move all of them over this fiber, over this divisor. So here I don't really need X to be one Fano variety. Actually, I can work on a family of Fano varieties. Then I only need the only difference is instead of X cross B, now I actually have this family of divisor and a family of Q complements. Then I just take the product over the base. Then the same argument, if you you say that we basically prove that this function, that basically the function is constructible. The delta function is constructible. It's basically, if you compute the minimum among all the points in the LC place over one disjoint component, it's a constant. But then you have a several constant. So the real minimum will be the minimum among all these different constant. But we know the image, all of them are constructible. So that gives me a constructible stratification of the base. So that's how it got the function is constructible. So, but actually we got one more property which we are going to use, is that now I move my divisor over one fiber. So each of them corresponding to a point. Then, of course, this infinite set of points in the dual complex, which is a compact set, I can take a limit. So the limit is a quasi-monomial valuation. The main disadvantage of this limit is a priori, the coordinates might be real numbers. So it might not be a divisorial valuation, but it's definitely much better than general valuation. And also you can show that you can actually extend the two function A and S continuously to this like a dual complex. So in particular, we know that this quasi-monomial valuation indeed gives you a minimizer of A over S. So if we extend this A over S to a larger set, we actually do have a minimizer to have. So I will use this factor later. So now we can, once we have the openness, we can at least talk about a stack. So first, it was a result by Chenyang. He proved that if I fix the lower bound of the volume and then fix the lower bound of the delta x, then all such Fano with a fixed dimension is bounded. So it's parameterized by a finite type base. And this boundedness can be reduced to the Berkas BAB type results. But later we actually show that using these two bounds, you can actually bound the Katia index of your Fano variety. Then actually, for this, we need something deeper local result, which I prove with Zichuan, which I'm going to talk about tomorrow, something called the normalized volume related to local stability. But for now, if we know that Katia index is bounded, then we know it's all the Fano is bounded even before the Berkas result. You can just use my result with Heiken and Makerna. But anyway, we know this boundedness with this openness, then we can start to stratify the stack of all Fano variety with a fixed dimension and a fixed volume, because that's two discrete invariants. So then then we basically get the consequence that I can start with 1, and then I have a infinite sequence of numbers, delta 0 larger than delta 1, which convert to 0. And the stack is that basically for each delta, there is an open stack, which is, I look at the Fano variety with delta invariant at least this number. And that open stack is a finite type Artin stack. So particularly if I choose delta to be 0, that's precisely the locus, which is the locus of K semi-stable Fano. So I write it as xk. So the K means K semi-stable. So we have this stratification. So if you study modular of vector bundles, so this is really like I consider the modular space of all vector bundles with the same rank and degree. And then there is an open part, which is a semi-stable one. And then you can actually stratify them using some function defined based on its Hadana-Shimhan type. And then you have this stratification. So each strata is open. Here also each strata is open. Now, of course, the total stack, it's unbounded. So if you don't choose delta 0 to be 1, if you choose smaller delta, you got a finite type Artin stack, but it doesn't behave as well as xk. There is some major advantage of the first one, the K semi-stable one, which I'm going to talk next. So that's topic today. So today, basically, I want to answer this question: that if I have a family of Fano varieties, what's a degeneration theory should look like? So in general, if I start with a family of KOT Fano varieties, we prove that we can always get a KOT Fano degeneration. But the problem is usually it's not unique. So there is no canonical one. Then you can start to assume that the general fibers are K semi-stable. Then you can ask yourself two questions: whether there always exists a K semi-stable degeneration. That's somehow like the properties of the moduli. And then you ask me that whether if it exists, whether it's unique. So that's actually the separatedness. So somehow you can ask these two questions. And if you just look at the Fano varieties, then you can answer the first one, but the second one you don't have an answer. It's very hard to find some class of Fano variety to satisfy both of these two conditions. But I'll show you that the K semi-stable one does have. So today I want to talk about the 3 topics. The first is good modular space. So I think this notion was already introduced in Matthias' talk. So basically, we look at the coordinate ring of a Fano, and we define a filtration, basically indexed by a real number, such that they are multiplicative. And the last property requires that the filtration, this is a decreasing filtration, and for each, basically, it's only non-trivial in a sector. So if it's below the sector, it's always the Rm. If it's above the sector, it's always 0. So it's only decreasing inside the sector. And because the multiplicative, you can either say the gradient ring is sorry, here it should be R dot is double gradient ring. First, there is a gradient by R by M, then there is a gradient coming from the F. And then we can similarly define the SM function, which is basically just looking at all the jumping number, and then you take the sum of them, and then you just divide by the dimension times n. So take the average jumping number. And so a typical filtration is basically the filtration induced by a vanishing order of a divider. So if I have a divider upstairs over X in some bidirectional model, I just look at the vanishing order, I of course got a filtration. But there are other more general filtrations will show up in our talk. That's why I want to introduce it. I mean, in particular, you say that the SM function for divider and the SM function for the filtration induced by the divider coincide. I mean, no surprise. So I want to prove that the limit of this SM function for any filtration actually has a limit. So basically, I can look at so for any fixed T, I can look at the sublinear series given by the filtration by FTM. You can easily check by the multiplicativity that this is also linear series. This is a multiplicative linear series. And then you can define the volume by just a standard way define the volume. And then you realize that if I look at the function, basically the FMTMRM divided by NM, it has converged to the volume, which is the volume divided by the minus k power 2n. And if I take the derivative of both sides, I have this like a weak convergence for distribution. So basically the distribution for the finite level one is just the sum and the jumping number after scaling. And another one is called the Dirichlet-Hickman measure. I mean, so that's why I write DH. That's a Dirichlet-Hickman measure for this filtration. So then if you integral, I mean, because you have this weak convergence of distribution, if you integral against the T, then on one side you got SMF. On the other side, you got the limit SF. So this is a definition. You can use this as a definition of SF. And then also you can check that, of course, this should be the same as SE when F is induced by FE. So to study this, I mean, there's a theory of a concave body, I mean, provides a very foundational tool to study this, which developed by Lagerfeld, Mustata, Kovansky. And this gradient of linear series one, I think was also in Buxton Chen's work. So basically, we want to define some function to test the K-stability for any filtration. So we know how to define for divider. So for filtration, of course, the SF plays the role of SE. So now the question is, what number plays the role of AE? So A is the log discrepancy. Of course, there is no way you can define log discrepancy for filtration. So there should be some other definition. So now we look at the base ideal, which fixed lambda. I just look at the linear sublinear series F lambda Rm mapped to Rm. Then this gives me an ideal, which is just a base ideal. And if I fix T, I look at that the IMMT along this direction, I also got a multiplicative sequence of gradient ideals. And then I define mu f. I mean, when this T is very small, then my I is always the entire ring. Then the LCT is of course infinity. If my M is very large, the ideal is 0, then the LCT is 0. So basically this LCT is a decreasing function on this T. So now I look at the supreme T such that the LCT is at least 1. And I call that to be the mu F. And then we define the dim functional of the filtration to be mu F minus SF. So the mu plays the role of log discrepancy for filtration. And we show that X is semi-stable if and only if the DF is always non-negative for any F. So this is another equivalent description of the K semi-stability, but now we test on a larger class of objects, which is the filtration. So filtration contains the valuations. Filtration also contains test configurations. So this is the largest class of objects which we look at. I mean, of course, Young and Buxong and Young, they might look at even more general objects, but this is the largest object we look at. So to get the, I mean, this equivalence, part of this result was really the definition, but the equivalence was proved by Fujita in 15, and then myself and Joy 20, because somehow, I mean, there is a development of the theory, which I don't want to go into, but that's how basically you should combine the work of these two. And actually, one direction is easy. So if I know the df is always non-negative, then of course, I mean, I should expect the a minus s for any divider is non-negative. This is easy because the mu is always less than the log discrepancy if the filtration is induced by the divider. I mean, that's just a simple exercise. The basic fact is because the v, if you take the value of v and the ideal sequence induced by this, for the filtration induced by this v, then it at least a t. I mean, this one is easy. The other direction is more complicated. So the original proof by Fujita was he basically approximates this f by some like a finite generative one. And then for this finite generative one, he showed that the Dean invariant also approximates. This is actually one of the very crucial points that the Dean invariant plays a role. Because the same thing doesn't hold in the Futaki invariant, at least we don't know. So I think for a while people work on Futaki invariant want to get this kind of result, but we don't have a lock. But for Dean invariant, Fujita showed this, that you can actually approximate any filtration by the finite generating one, and also in the same process, Dean invariant also approximate. And then for finite generative one, you can construct a test configuration. Then you can prove that the Dean of this finite generative filtration is larger or equal to the Dean of the test configuration. And then because the test configuration one, we already proved it's equivalent to the valuation one, then we got all the df has to be non-negative because all the Dean f has to be non-negative. So another proof is we found later is that I can actually find the valuation which computes the LCT of this sequence, precisely the sequence given by this mu. And then we show that the D of the F is actually larger or equal to the A minus S for this valuation, but with some scaling. So after all, the version we define K-stability using divider, using test configuration, using filtration, they are all equivalent, although to prove the equivalence it actually requires some deep work. So now I want to use this filtration version to understand the modular problem. So I want to first study the uniqueness. So my setting is I start with x over some dvr. So I write as spec O. So with a fraction field k, and I let E be a divider over this x. So now if I look at the push forward of minus mkx, it's O module, it's a gradient O module. And the E, of course, will induce a filtration on this module. And then if I look at the map from AM to RM, then I look at the image of this filtration induced by E. Then this way, I got a filtration on the gradient ring of the central fiber. So the module AM mapped to RM, and I have a filtration on AM. I just look at the image of this under this map. Then I got a filtration on RM. So that's what I call G. That's why I didn't write the F. I write a G because I want to remind you this is not from the E over X0. It's E over the ambient family, and then I restricted the filtration. So particularly that's why now you say why I need the notion for general filtration, because my filtration is from some filtration restricted from the the one induced by divider, by itself might not be induced by any divider on the special fiber. So if I have another family X prime, which is basically isomorphic with X over the genetic fiber, now I want to understand them, right? This is basically how to understand the uniqueness. So I assume they are the same on the over the puncture disk over spec the spec K. So I have two invariants A, which is the discrepancy. So for the second family, I have a central fiber. So I regard that as a divider of the first family. Then I can compute the discrepancy. And that's just going to be the log discrepancy minus 1. But that's, if I add x0, that's precisely just the log discrepancy of the AX0 for x0 prime. So this is easy. And similarly for A prime, I can define this way. And then for this x0 prime, I can use the above definition to get a filtration of G on the central fiber of the coordinate ring of x0. And similarly, for this x0, I regard it as a divider of the second family, and then I got a filtration of the coordinate ring of the central fiber of the second fiber. So the main key observation is there is isomorphism between these two gradient rings. I mean, there is a shift of the grading as I wrote, but they are isomorphic. I mean, once you notice this isomorphic, if you give access to a student, I think he probably can prove it. But somehow it took us a very long time to realize this isomorphism. Somehow, I have a two family, I have a two fiber, then their gradient ring actually are isomorphic if you define the gradient like correctly. So because of this, then I know SG plus, if I compute the x0 for the G, and compute the G prime for x0 prime, then I know the sum is A plus A prime because it's isomorphic. So to understand this isomorphic, I draw a picture. So somehow, if I have a sections, I have a very high order toward the valuation of x0 prime, and then I blow up, I get rid of the x0 prime, and then I go to the other model, they are somehow separated, and vice versa. So I draw a similar picture to help you to understand this isomorphism. So that way I got the 2s, the sum is always A plus A prime. And if I compute the ideal, because the ideal is essentially just introduced by x0 prime. So if I look at along the line, which is the log discrepancy of this x0 prime, then I know that the LCT is at least is at most of 1. So particularly, I know that the mu g is at most the log discrepancy. And similarly, I know that the mu g prime is at least the log discrepancy of A prime. So far, I don't use any K-stability yet, but now I'm going to use it. Because remember, K-stability tell me mu minus s has to be non-negative. And this holds for both x0 and x0 prime. But I know s plus s prime is A plus A prime. And the mu is less than A. Mu prime is less than A prime. So if both of them are K-semi-stable, the only thing this can only happen if A is equal to mu g equal to Sg, and A prime is equal to mu g prime equal to Sg prime. So the semi-stability, K-semi-stability basically force all the inequality we have now is actually equality. That's where the semi-stability plays a role. And then particularly also we got that the LCT along this ideal is not less or equal to 1, it's actually precisely 1. So that tells me what? That tells me the x0 prime indeed computes the log canonical threshold of this ideal sequence. So then from BCHM, we know that the x0 prime induces a finite generated gradient ring over AM. So we got finite generation from this. In general, if I have a two family, I have a second, I have a two family, I use a second central fiber to induce some filtration of the first one, there is no reason why it should be fine generated. It's just some divider upstairs. But here we just have fine generation. And then because the induced, then if you take the quotient, now work on the central fiber of the first family, you also have fine generation. And vice versa. So you have fine generation for the another G prime for X0 prime. So what tells you that the X0 and X0 prime, both of them degenerates to the purge of this fine generative ring. And the weight action is actually opposite to each other. So particularly then you got the photonic invariant is also opposite to each other. But again, X0 prime are K semi-stable. If the photonic invariant are opposite to each other, then both of them have to be zero. So particularly that tells you that the central fiber is also K semi-stable, because we know that if I have a K semi-stable object with a photonic invariant 0 degenerate to something else, then that guy, central fiber, is also K semi-stable. So then this is the result I proved with Bloom, like in 2018, that if X and X0 prime actually degenerate to the same K semi-stable fiber. So actually the uniqueness for K semi-stable, for the K-moduli Fano is not that they have the same central fiber. They actually, the uniqueness is they degenerate to the same thing. But this is a picture we expect in the vector bundle case as well, right? If you have a two semi-stable filling, they are S equivalent. So this is the corresponding S equivalent. So actually, I want to enhance our understanding of this picture. So I draw that this STO, which is the stack of OST, module GM action, OST with ST equal to pi. Pi is the parameter of a uniformizer of O. And the action is T2 mu T S2 mu inverse. So there is one central point, 0. So if I take a STO, I take out this point. Then I just got two copy of spec O glued together. So, okay, I really hope I can have my pen, but no, no. Anyway, so if I over STO, the base is just the first picture. The base is like two curve, but double pointed. Since now I have X and X prime, each defined over the spec O. Then I have a family over this gadget, STO, take out to this point. And I also know that now I constructed something such that the X0 and X0 prime degenerate to. So this X0 and X0 prime correspond to the locus, which is S equal to 0 and T equal to 0. So you have this two X0 and X0 prime. And then, so if you glue this family together, actually I construct a family over this STO. So somehow, originally, we have this 2 point, we have this family over the 2 point, and we have some degeneration, but actually all this data can be put into one equivalent surface, over one equivalent surface. That's the STO. So basically, essentially, that's what we prove. So here then comes this great theorem by Harper-Leister and Henlos. So they basically prove that a stack, they define a stack is S complete is precisely what I was saying. That if STO taking out this point and map to this stack, then it can be uniquely extended to a map from this STO to this stack. So you basically if I have a equivalent puncture surface, I take out one point, map to this stack, then it can be extended to a map from this stack to this equivalent surface to this stack. And there's another similar definition called a theta reductive is that now I actually look at the O cross A1, but modulus GM action. Then there is again one special point which is corresponding to the closed point with the coordinates 0. And if you take out that point, you again have an equivalent surface, puncture equivalent surface. If that map to a stack can be always uniquely extended to a map from the entire surface to your stack, that's called theta reductive. Then there comes this notion called good modular space. So for stack, which, probably you heard this famous theorem by Kilmore that a separated Delimonfort stack has a coarse modular space. That's a nice theorem, but that only deal with Delimonfort stack. So now I'm dealing with a much more difficult stack, which is the Arden stack, which I have an infinite automorphism. So the best that you can expect is something called the good modular space. So good modular space basically says that this stack has a morphism to some algebraic space, such that at a local, if I take the at a local neighborhood of the algebraic space, I take the base change, then this is just given by the standard GIT morphism, which is a spec A more G mapped to the spec of the invariant ring. Here, G is a reductive group. So basically, the good modular space of a stack just say that this map is locally covered by this like a standard GIT type morphism. I mean, this is the best that you can expect for modular stack. And the nice theorem of upper Haber-Leisler and Henlo say that if your stack is a fine type Arden stack with a fine diagonal, I mean some standard condition, then it has a good separated good modular space if and only if it's S complete and theta reductive. So here I would say that for the Remarkably stack, I think many times if you have a Remarkably stack, it's separated, then you do have a cross-modular space. For Arden stack, it's very rare you expect your Arden stack has a separated good modular space. If it does have, that means you are in some like a quite deep modular problem, and K-stability is one of them. So basically, Upper Bloom, Haber-Leisler, and I, we prove that our stack satisfies the S completeness and the theta reductive. So as a consequence, that it has a separated good modular space. And the point precisely corresponds to K-stable Fano varieties. So if you are working over C, we do have a good modular space, which the C points are precisely the Kähler-Einstein Fano, but this is constructed algebraically. And to prove the proof of its S complete is essentially the proof I just outlined to a few slides ago. And the theta reductive, I mean, the proof is somewhat similar. But actually, as a corollary, we have this that X is K-polystable. Then the automorphism group is reductive. I mean, you heard this in Buxton's talk. I mean, that the constant scalar curvature will imply the automorphism is reductive. I mean, we don't know how to prove this for general polarized variety, but for Fano variety, we actually know that the algebraically, if you assume it's K-polystable, then the automorphism is reductive. I mean, this actually was asked for many years, but really until we find this good modular space, we prove it. And you might wonder, like, want to compare what's the point? I mean, study since we have this modular space, you might, of course, want to study the non-algebraic closed point, point over some non-algebraic closed field. And then theorem by Zhuang tells you that actually to test the semi-stability or polystability over a field is the same as to test it over its algebraic closure. So basically, there's no difference to test whether on the field itself or on the algebraic closure. Okay, next I want to talk about the higher rank fine generation. So the first one, settle the good modular space part. So the theorem I prove is Yu Chen and Zhuan Zhuang, and then we have a stronger result 1 year later with Zhuang, is that if a Fano variety with delta x in this range, then for any cosine monomial valuation, compute this delta x. I mean, 20 minutes ago, I showed you that there is always a cosine monomial valuation. Actually, you can prove any minimizer is always cosine monomial. So if there is a cosine monomial valuation, compute this, then it's always finite generated. The gradient ring is finite generated. So once you have this, you can show that if it's the gradient ring is finite generated, if you look at this like a neighborhood of V in the minimal rational space contained, this QM, this thing, this space of cosine monomial valuations, it has a rational structure. If I look at the minimal rational space containing of V, then both A and S will be linear in this neighborhood because of this finite generation. I mean, the finite generation will imply that A and S are both linear. So of course, if A divided by S, take a minimum at a point, but it's actually linear in a neighborhood. that means that actually it's a minimum along all these points. So particularly that implies there is a rational minimizer, which gives you a divisor. So that means under this condition, you do have a divisorial minimizer. So particularly if you assume your X is K-stable, where a priori you only assume A is larger than S for any E. Then because one of them will compute the infimum, then actually the A is larger than uniformly larger than S, larger than 1 plus epsilon for some S. So now I want to explain the finite generation. This is probably one of the most difficult theorem in the entire theory. So, I already show you that the minimizer is the LC place of a complement, Q complement. But we know in the divisorial case, this will already give you finite generation by BCHM. However, this is not true in the monomial valuation case. So actually, if you just consider a very simple example, it's P2, C. C is just the nodal cubic, so it's the alpha curve. Now, of course, all the LC place is the weighted blob of this two branch of this. You take one branch to be one branch to be T. And you ask yourself, when the gradient ring is finite generated? So as I told you, if it's a divisor, that corresponds to the T is Q, it's finite generated. That's fine. But then if it's irrational, it's finite generated, if and only if it's in this strange range. So somehow, I think before you can calculate it, I think no one can predict that this how to find this range. We really find this range by calculation, and actually Junyao Peng proved that this similar picture actually holds for the polar surface with any irreducible nodal one complement. So this is not something happen like very rare. This is happen very often. So if I have a valuation which is LC place of a complement, usually there's no reason. If it's not divisorial, a priori there is no reason it's finite generated. So we have to sort out the final condition than just being a LC place to guarantee the finite generation. That's what I'm going to do. So there are basically 3 steps. So the first step is I want to show V is not just an LC place. It's actually an LC place larger than any arbitrary divisor G. So this is a step 1. So basically, the fact that it's being a LC place, it's being a minimizer of A over S, actually gives me a little bit of flexibility to say it's not just an LC place. It's an LC place for some divisor, but the divisor can contain a little bit of adding up to other divisor. And the proof, okay, I don't have that much time, so I'm probably not going to explain all the details of the proof. But basically, we want to do some like integral Diophantine approximation of this vector corresponding to this valuation, and then we basically work on this model, and then we apply global ACC. So this part is fine. Then starting from this log resolution, we have this V there, and we have this value, this complement. Then we can use a minimum program to show that actually V is on some other DLT model, but this DLT model is log Fano. So we actually have a log Fano DLT model, such as the V is a LC place of this log Fano model. This from 1, this extra divisor, we can get this 2. And then, for log Fano DLT model, you can easily prove that the dual complex is a simplex. Then we prove that if I have a 2 valuation in the same phase, interior phase of the simplex, then the gradient ring are always the same. That because each phase contains some rational one, for rational one, we know it's finite generated. Then we actually know everyone is finite generated. And this is actually quite hard, this one. We have to compare 2 filtration. You have this filtration, for any fixed alpha, you have this like a filtration given by this V alpha. But you have this like a somewhat naive filtration that I just weight the vanishing order of section along this each coordinate using my alpha, and I use this to be the filtration. And of course, the naive one is smaller than the real one V alpha. And we know that if the naive one, the gradient ring is integral. So integral means you can show it means it's induced by some valuation. Then it has to be induced by the same valuation V alpha. And for this naive one, it's much easier to prove it's finite generated. So you have two tasks. So you first prove the naive one is finite generated, and then you prove the naive one, the gradient ring is integral. Then you are done. Because that naive one will be the same as the V alpha. So now how to study the naive one? So basically, we want to show that I have this gamma 1, gamma 2. I want to show that this I gamma, this R gamma, indeed give me a family over AR by using them degenerated step by step. And then you might ask, I mean, there might be an order choice of, whether I first take gamma 1, then gamma 2, or first gamma 2, then gamma 1. In this case, actually, they are the same. The gradient ring are always the same. This is also non-trivial. I mean, if you have a two divisor, the gradient rings are same. But if you graded them twice, the gradient rings are same. But if you have a three, then usually it's not. But this one, we actually, no matter how many you have, the gradient, the multi-gradient ring, it's always the same. And the reason is actually this multi-gradient ring is a central fiber of some family over AR. And this family is locally stable. And then, so this family, a priori, I have this divisor. I can define a family outside all the codimension 2 locus of AR. So here locus are just the coordinates, bunch of them are to be 0. That's what I mean by locus. So for each divisor, I have a degeneration over the open part, which is the torus times A1. The original X is defined over the torus. And for divisor, you actually can extend this over the torus cross A1. And you take the R of them, not cover all the codimension 1 locus. But the question is whether you can extend them to the codimension 2 locus or codimension higher locus. And if you can extend them, then that gives you the uniqueness. And also that tells you it doesn't depend on the order. Because if I want to extend this family over codimension 2 locus, such that the fibers are of the same dimension, then there is a unique way to extend that as a polarized variety. So this is the behind the reason why the order doesn't matter. Because no matter which order you choose, you basically extend your family to be a equidimensional family over the AR base. So they got to be the same. So okay, I mean, it's somewhat technical to prove that you can do this. The upshot is that you just don't want to extend the family. You actually want to simultaneously also extend the DLT model above it. So you actually prove that you have this family of X simultaneously with you have this extension of the DLT model above. And because above the DLT model, which particularly implies the fiber is KLT, which particularly implies the X is integral, which particularly implies that the F alpha, the gradient ring is finite generated. So somehow, sorry, not finite, it's integral. So somehow you really have to work pretty hard with these two models and use like a very subtle. I mean, it's relatively easy to show you can extend the family as log canonic family, fibers to be log canonic. But to show the fibers are DLT, it's way more subtle. And okay, I think I'll skip the proof of this part. But as I said, this is actually one of the most challenging part of the story. But I want to mention that there is a recent in progress work by Ziyuan Chen. He showed that indeed the gradient ring can be realized as a Cox ring of some Bayesian model of the minimal center of the Y. So if you take the intersection of all the gamma I, you got some Z. And the gradient ring indeed is some Cox ring over this for some model they prime over this Z, and of course the Cox ring of integral variety itself is integral. This way also prove the integrality, and so the last part I want to prove the properties, and which heavily relies on the high rank finite generation, which I just showed you. So basically, the result is the separated good modular space is not only separated; it's actually proper. So in other words, this settles the problem that if I have any family of K semi-stable Fano variety, I can always over a puncture disk, I can always fill in the limit with a K semi-stable Fano one. And the previous term tells you if you have two fill in, that they actually degenerate to the third one, the same third one. So both of them will fundamentally depend. So there are two proofs. One is given by Bloom, Haber-Leisler, and Liu, like 5 years ago, and the one which haven't the paper I think we will post it in a few weeks is with Bloom, Liu, and Zhuang. But both as two proofs need the high rank finite generation. I just talked about 10 minutes ago. So somehow this high rank finite generation is indispensable to deal with the purpleness. So I mean you can regard that the high rank finite generation is a major part to settle the compactness of the K polystable problem. I mean, for this, that's also the main part to prove that the uniformly K-stable is the same as K-stable. So, but anyway, once you have this higher rank finite generation, so how do you get to the properties? So there is one theory by Haber-Leisler called theta stratification. So basically, theta stratification tells you if I have a stack if I have a modular stack with also unstable objects, if the unstable one has an optimal destabilization, unique optimization, that actually will imply the good modular space itself is proper. So if you have some information on the unstable one, then the good part is, the stable part is also proper. So this is like that in the Kempf theory for vector bundle. So if you know this like a Kempf net theory for vector bundle, you actually conclude that the modular of vector bundle is also proper, of stable one is proper. But somehow to get this theta verification, you might think I just use the Futaki invariant divide by the minimum norm, defined by delta is enough. But that's basically the delta minus 1. However, this is not enough because for Haber-Leisler, he really needs the optimal destabilization is unique. But as I said, usually if you look at the divisor which computes the delta, usually it's not unique. So you have to make an alphabetical order such that among all the E which computes the delta, you have the second function, which is a Futaki invariant divided by the L2 norm. And then because the first one will guarantee you work in the finite dimensional space, then the second one will behave more like a GIT problem. And then in GIT, we know that the functional divided by the L2 norm always has a unique minimizer. That's basically what Kempf proved. So if you prove this to alphabetical order, you can say stratification. So the disadvantage of this proof is it's really not clear to us. I mean, if you have a family of K semi-stable Fano, what is the feeling? It tells you can start with any KOT Fano and use this theta stratification theory. You can improve your central fiber each time with this constant. After 5 steps, you got a semi-stable Fano. But what's the geometry look like? Even the replacement, the geometry is explicit geometry is not clear. We just know the existence from this theta stratification theory. So after saying that, let me just say that originally we built up somewhat like a relative stability theory for family of Fano over DVR. And we define relative delta, which is the A of the family of E divided by the S of the E, which I defined before, the restrictive GE. But here it's not just AX. Actually, I can give me a little bit of room by considering 1 minus TX0. And if I choose T to be 0, then you can prove that the delta X of this family is actually just delta X0. So if I choose the coefficient in front of X0 to be 1, then the delta there, the relative delta is actually just delta X0. But now we can work for delta larger than 0. And we show that, again, use higher rank finite generation, we show it's quasi-monomial minimizer, which then is finite generated. And then we actually show that the minimizer, you can set another family with the same generic fiber, but with different central fiber, such that the central fiber basically is coming from the minimizer of the relative one. And then I have this sequence. So all of the first 4 are trivial, but the last one is very subtle. So that's why I put the red color. And we prove that after this process, the relative delta is actually less or equal to the delta of the filling of the central fiber. Okay, I'm not going to talk about the proof. Thank you very much.